So right now we're almost ready to get into the first law of thermodynamics. Okay, we're almost there. We've been talking a lot about property information. We've been learning to look stuff up in tables, right? We've been looking stuff up in tables, looking up things like pressure, temperature, specific volume, internal energy, enthalpy, the H, remember? We've been looking all that stuff in tables. That's going to help us right here in the first law. I have the first law for closed systems right here. We're going to be looking that up. Those U's, a lot of times those U's, or maybe they're H's later on, we're going to be looking those up in tables a lot of times, or using something else here I'll mention. The other parts are kinetic energy and potential energy, and a lot of times those are going to be small, okay? But recall that the Q in this formula here, that's heat transfer. Recall, that's heat transfer. And the W is work. Okay, and that's what we're going to talk about today, mainly. We're going to talk about work. Thermodynamic work. And other forms of work as well. Okay? But we've been spending so much time looking stuff up in tables because we've got to be familiar with our property tables so that we can look up our U's. We've got to be able to look up our U's and later on look up our H's. We've got to be able to look those up in property tables. We've got to get that to apply the first law. But then there's heat transfer and there's work. Now, as I mentioned before, heat transfer has its own separate class. So in this class, you're never going to calculate heat transfer apart from that equation. That equation is pretty much the only way we're going to get heat transfer. That's all we know. First law. The only way I can really solve for heat transfer is apply the first law. Not really another way. I mean, maybe later on we might have a little bit of something here or there, but not much. It's mainly going to be first law. But the work equation, that one we have some more stuff, and that's what we're going to talk about today. But let's fill out a few things here before we get to it. All right, we learned last time internal energy is a property. Okay, it's a property. What does that mean? Property just means you can look it up. And it can be found two different ways. We can use the tables. Okay? Or we can calculate the change in internal energy using specific heats. Okay? That's it. And that's what we did last time. It's been a while, it's been a week, but we looked and we used specific heats to calculate the change in internal energy. Or we'll use tables. One way or the other. One way or the other, we've got to calculate U2 minus U1. Okay, tables or specific heats. The Q, we really can't do anything but use the first law. Okay, and then the W term. That's the other term we've got today that we've got to focus in on. Okay, so we got to talk about work. Now, there's different types of work, as I mentioned before. There's mechanical work, there's electrical work. But in thermodynamics, there's an equation that defines work. This is so fundamental that I kind of expect that you'll memorize this. But thankfully, it's so simple. Work is equal to the integral of pressure, P, dV. Pressure, d volume. That's the fundamental equation for work in thermodynamics. If you don't remember anything else about work, I hope you remember that's the integral of P dV. At least do that, okay? Thermodynamic work, okay? So it has to do with pressure, and it must have to do with volume. Those are the two things it must have to do with. Pressure, volume, okay? Now, let me help you get a little understanding of this. I want you to help you understand this a little bit. I want to envision a piston cylinder again. So here's the piston inside a cylinder. And let's imagine that it has pressure P inside, all right? And that pressure P is pushing up on the piston here. Okay? In fact, the pressure P is pushing up on the piston such that it went up a small amount ds. So the pressure P pushed up on the piston such that it pushed it up a small amount ds, an incremental amount. That's what I want us to think about. Okay? Now this is a piston cylinder, so it has a cross section. Let's imagine it has cross-sectional area A. That's the cross section. Cross-sectional area A. Okay? Now, here's what I want you to remember. You've learned this. You're probably looking at this in dynamics now, physics, things like that. You probably recall that work is equal to force times displacement, right? Fs, force times displacement. It's really the integral of force dot displacement, but you know, it's really force times displacement. But you can also define the differential amount of work at dW. Let me write this a little better here. Yeah, dW is equal to F ds. Oops, not dx, ds. Right? That's just differentiating both sides. So a differential amount of work is force times a differential amount of displacement. Right?
Okay, so what's that mean? Derivative.
Yeah, it's almost same thing. Derivative. This is like a finite difference. Instead of derivative is like infinitely small, but it's the same idea. So yeah, finite small amount of work. So it's basically the same. Okay. Now, remember what pressure is. This is a very simple derivation. Remember what pressure is. Pressure is a force divided by an area, right? If pressure is a force divided by an area, what's a pressure multiplied by an area? What's P times A? Force, right? That's easy. Obviously, I'm not making this hard. Therefore, P times A is equal to force, okay? Therefore, if I look at my equation down here, I can say differential work is equal to force times differential displacement. Force is equal to pressure times area times differential displacement. Okay? And then the last thing is, if you have a cross-sectional area that undergoes a differential displacement, a small amount of displacement, you have a differential volume. So this really is the same thing as P dV, because area times displacement makes a volume, right? A little volume. Okay? So basically what I want to do is connect what you already know about work, force times displacement, to what we know about thermodynamic work, which is really pressure times volume. Okay, it's really a pressure times a volume. But we are going to calculate it formally as integral P dV. Okay, that's really the formal way we're going to calculate this. Okay, now, as I promised you, we won't be doing a lot of difficult math. Okay, the math's not going to be hard, I promise. In fact, we really aren't going to apply this equation too much straight up. Okay, we're going to make it easy. Okay, I don't want to apply that straight up. And why make it harder than it needs to be? Okay, we're going to simplify this. Okay, we're going to simplify this under the following assumptions. Okay, one of these few cases is going to happen a lot. Okay, first often, constant volume process. Okay, if work is equal to integral P dV and dV is equal to 0, what do you think the work is equal to? If there's no volume change, 0. Yeah, exactly. And that's the case here. When you have a constant volume process, you have no work thermodynamically. You have no thermodynamic work for the constant volume process. That's easy. Okay. By the way, cases which you'll see this are, technically, do you remember, does anybody remember, I talked about this last week, the term for a constant volume process? It's a hard one to remember. Isochoric. That one is hard to remember, okay? But let me give you another clue when it's going to happen. Sometimes the problem will say it's an isochoric process. Okay. Other times, instead, it'll just say something like rigid tank. See, if it's a rigid tank, if it's enclosed in a rigid tank, the volume of that tank is not going to change. And the volume of the tank's not going to change, and then it's a constant volume process. So you'll see that happen a lot too. Okay, how about the next one? This one's also very simple. Constant pressure process. In this case, work is equal to integral P dV, like always. But if it's a constant pressure process, how can you simplify this integral? If P is constant, how can you simplify the integral? Pull it out, right? You learn that in calculus, right? If you have a constant, you don't have to keep it in the integral. So then what you really have is this, right? You really have P integral dV. Well, in that case, we can simplify. Work for a constant pressure process is pressure times V2 minus V1. Oops. Okay. Constant pressure processes happen a lot. The good news is case 1 and case 2 happen a lot. Constant volume process, that happens a lot. Constant pressure processes, that happen frequently as well. So good news, we've got 2 of them here that are going to help us a lot. Okay, so that's good. That's good. That's going to make our life easier. All right, both those cases, and both of them are pretty easy. Okay, to calculate the work for a constant pressure process, it's just pressure times the volume change. That's it. That's easy. Okay, all right. So those 2 happen a lot. Now, the next ones, well, these next 2 are very highly related to each other. They happen probably not as much as case 1 and case 2, but we certainly see them some. Okay. All right, so I got a new term for you. Sometimes we have polytropic processes. Okay, here's another term I got to throw at you. Okay, a polytropic process is one where pressure times volume to the nth power is equal to a constant. Pressure times volume to the nth power is a constant. Typically, n is given to you. Okay, so I'll make a note. Any number. Typically n is given. Okay? Generally, the range of n is around 1 to a little bit greater than 1. Maybe 1.1, 1.2, 1.3. It could be higher, but you know, it's generally around there. Okay? It's generally not less, but I'm sure it could be. I'm sure there are examples. Okay? Typically, n is given to us in the problem. Okay? A polytropic process simply means that pressure times volume to the nth power is a constant. Okay? Now, there are some special cases of that, and one of them is number 4 here. Okay? But when we have a polytropic process, generally the problem's going to say you have a polytropic process. Okay? So, you know, it's not going to be too much in disguise, okay? Now, when you think pressures and volumes, any equations might come to mind that we've been talking about recently? Multiplied to each other, P times V, ideal gas, yeah. Oftentimes, the polytropic process might be related to a process involving an ideal gas. It could be, okay? It can often be related to a process related to an ideal gas. Not always, but oftentimes that's true. Okay, now, you don't have to memorize these formulas, but I'm going to give you two formulas for the work in a polytropic process. They're going to be on your equation sheet, of course. The problem is I'm not going to label them on your equation sheet. Oh my goodness, here's the polytropic process equations. Okay? So you still do need to have the mental relationship between those equations and what they do. That's all. Okay? So for instance, we have to break this up though. We have to consider two cases. One where n is not equal to 1. When n is not equal to 1, you get the following work relationship, thermodynamic work relationship. You get work is equal to mass times R, the gas constant, T2 minus T1, divided by 1 minus n. And you can tell why n cannot be equal to 1 in that equation. You can clearly see n cannot be equal to 1 there. Okay? So there's an equation for a polytropic process. How? Yeah, oh yeah. Yeah, now of course in that case, if you really want to get picky there, it doesn't really matter, right? T2 minus T1, it doesn't really matter. But in general, you know, when you're using equations involving temperature, think absolute. So you got that. Now, of course, I said there must be an equation when n equals 1. Of course. So you have, in the special case, when you have a polytropic process with n equal 1, you get the work is equal to P, V, ln, V2 over V1. Now you might notice that I didn't label P and V. Well, with n equal 1, P1 V1 would equal P2 V2. So it doesn't matter which PV I put in there. I can put P1 V1 here, or I could put P2 V2. It's the same thing, right? As long as n equals 1. I think it won't be that hard for you to remember these equations, where to find them. I mean, not memorize them, but where to find them on your equation sheet. Because if you think about it, this equation has an n in it. I think the only time, well, not the only time, but nearly the only time we use this, for work, it's pretty much the only time we're going to use this. We will use n in some other equations later, but they're not for work, okay? So the only time we use it for work is this equation, so you hopefully can go, oh yeah, that's that polytropic thing, because it's PV to the n is a constant. Then you got this one, which has a logarithm in it, so that might be a little bit different as well. And you hopefully remember those. Oh yeah, those are those polytropic ones I got to apply. Obviously, the key thing is to practice. Homework, practice in lecture, practice the problems. Okay, that's the key thing. All right? Now, one special case that actually turns out to be something like this, we will see this happen sometimes, is if we have the isothermal expansion of an ideal gas. Remember the ideal gas equation. PV, the one form looks like this, right? PV equals MRT, right? Well, if you have an isothermal expansion, what do you think isothermal means? Constant temperature. Yes, constant temperature. If you've got a constant temperature, what you're really doing, let me take this equation here and solve it for temperature. It would be PV over MR is equal to T, right? That's just simple algebra. Well, remember that mass, this is closed systems we're talking about here. So for closed systems, mass and R are also going to be constant. So since M are also constant, what you really have here is P1V1 equals P2V2, right? Because if PV over MR equals T, but T is constant, right? So PV over MR equals PV over MR for each case. So obviously P1V1 equals P2V2. Well, this is basically the same thing as what we had in case 3, right? This is what we already done this problem. So when you have an isothermal expansion of an ideal gas, you have a polytropic process. So this is case 3 as above with n equals 1. Okay? So that's a form of that. And therefore, you already know the work, right? We already know the work right there. I don't need to write that equation down. You can just kind of draw an arrow and go, yeah, that one. So if you have an isothermal expansion of an ideal gas, bang, right there. You got it. Okay? It's going to take us some practice. It's going to take us some time. We've got some new equations, some new stuff here. And all of a sudden, when you start thinking about all the stuff I've thrown at you over the last few weeks, you start to realize, hopefully not too much, but start to realize, this is kind of intimidating. There's a lot of stuff to absorb. You're starting to get why people freak out with thermo, okay? I don't want you to freak out, though. We're going to take our time. We're going to go through some examples. We're going to start working with this. And the best thing you can do for yourself from now to the exam is to do homework and really put your time into it. Understand these different ways in which we calculate things, okay? Now, my last note's an important one. These equations calculate thermodynamic work. It doesn't mean it's all forms of work, okay? There may be other forms of work, like electrical work or mechanical work, okay? So just because thermodynamic work is equal to 0 doesn't mean that all work is equal to 0, okay? There's different things, all right?